Tuesday's class, the critical numbers are, they're actually where f of x is defined and f prime of x equals 0 or does not exist. So in other words, a critical number doesn't count as a critical number if the function doesn't even exist there. So we're really looking at, you know, as the function goes along, these important points are where the derivative is 0, right? That creates a kind of potential min or max. And that can also happen where the derivative is undefined, right? Maybe there's a sharp corner. That's another way you could generate a min or a max. And then, of course, sometimes the derivative is 0 and it's neither a min or a max. So, you know, we want to understand the relationship between critical numbers and minimums and maximums. They're like potential minimums and maximums. But like this question here, sometimes they're just asking you to find the critical numbers. That's it. So I want to notice for this situation what the domain of the function is to start with. So what you want to notice here is that this negative exponent would be, and so this function is not defined at x equals 0. So x equals 0 can't count for us as a critical number. And that is a little, you know, kind of detail that is important. Just things can still happen at 0, but not on the function, right? And if the function doesn't exist at that point, then that point can no longer be a relative or an absolute maximum because the function doesn't even exist there, right? It's a hole or an asymptote or something of that sort. So it's always a good idea to think about the domain of your function before we jump into the problem. The next step is, you know, in order to find critical numbers, I want to figure out where the derivative is 0 or undefined. So I want the derivative of this, 1/3 x the negative 2/3, and then that becomes plus 2/3 x to the minus 5/3. It may look sort of terrible, but if you rewrite it with positive exponents, that's certainly going to be an improvement. And it's also going to help me see, you know, potentially x equals 0 would feel like a critical number because the derivative is undefined, but remember 0 isn't even a part of our function. So that one's not going to be a critical number. I do always encourage you to look at where the derivative is undefined first, and then figure out where it's equal to 0 second. A lot of times when we got into the work of figuring out where it's equal to 0, we would forget to go back and check to see where it's undefined, right? So my routine is to say, what's the domain of the function? Take the derivative. What's the domain of the derivative? And then finally, where is the derivative equal to 0? And whenever you have, so there's some standard equation solving techniques, and one of those is anytime you have fractions and something equal to 0, just multiply through to clear out the fractions. So I'm going to multiply by 3x to the 5/3, right? That's the largest factor that I have in the denominator. So you give me a 0 here. That's going to cancel with this, which will give me a 2. The 3 will cancel. Then 5/3 divided by 2/3 gives me x to the 3/3 or 1. And, you know, in this case, certainly that makes a big difference, right? X equals -2. So there's a couple pretty typical things here with the positive negative exponents. You got to be careful how you use those and work with those properly. And then also whenever you have something with fractions, right? We want to get rid of the fractions. It won't always be quite as easy as this one, but it'll certainly make your problem better to work with. So in this case, -2 is going to be our critical number. Any questions on that one? Okay. Other questions from the homework?
I have one question.
Yeah.
It is the last one, number 18.
Yeah. Yeah.
Yeah, I was not able to find the answer also.
Okay, let's take a look. This is also a good question to look at. And again, it may be slightly different depending on your version. Here we're trying to find the absolute max and min. So it's a different kind of question, but the critical numbers are the kind of crux of the problem, right? If you have the critical numbers, then we can find the absolute max and min. But there is also some theory that we talked about on Tuesday about how this works. And so the idea is that this function, because it's defined, natural log is defined for anything positive, and x is defined everywhere. So these are both continuous functions for the interval 1/2 to 2. Since they're continuous functions on a closed interval, we know the absolute max and min occur. That's the extreme value theorem. You wouldn't be asked this question at this point with a discontinuous function. That would maybe feel a little bit like a trick. But in the future, we do need to think about that. So it's good to practice now. So you don't necessarily have to write all that down, but you should recognize it goes back to checking the domain of the function, right? So when I look at a function, I intuitively just think about, okay, is that defined everywhere? If not, then I'm going to be a little bit worried. I actually don't care about everywhere here. I only care about 1/2 to 2. So then the question is, how do I find the absolute maximum and minimum? That happens, remember our theory there is that the absolute max and min can only occur at either the endpoints or the critical values. The critical values, remember, because if you have a local min, it has to be a critical value. Also remember that endpoints are not local maximums and minimums, because when I look at an endpoint, I can't compare what's happening on both sides. So like, I don't know what's happening over on this other side, so I don't know if this is actually a local min or max. In order to qualify, I have to be able to look on both sides. An absolute min or max doesn't have that requirement. It just needs to be the biggest value. So that's why, and it's also sort of important by a definition standpoint, because if this counted as a local maximum, this very likely is not actually a critical number of the function. Like maybe the function just continues on. The derivative is not 0 or undefined here, in which case then this would sort of fail our definition or our theorem that says local mins and maxes have to be at critical values. So there's also, it's set up that way a little bit because of we've defined it that way so that it fits with our theory, I guess. So, okay, back to the question. I'm interested in the critical numbers, especially. So derivative of x is 1, derivative of the natural log of 7x is 7 over 7x. So that's 1 minus 1 over x. In order to find the critical numbers, remember we first look at where it is undefined. It's undefined at x equals 0. It turns out 0 is not part of the domain of this function, so it actually isn't a critical number. And even more importantly, 0 is not in my interval 1/2 to 2. So I don't even care about looking at it because it's not in my interval. But even if I did want to look at it, it's not in the domain of the function. The natural log of 0 doesn't exist. So that's not a critical number. This is defined everywhere else. So now I set it equal to 0. However, you're going to multiply through to get rid of the fraction, or just you can see it that x has to equal 1. That is in my interval, so that's a critical number I care about. That's a potential absolute max or min. Once you have the critical numbers, you have the endpoints. It's now, I call it brute force. So I'm not really considering or analyzing what's happening with these. I'm just plugging them in. Whatever function value is the biggest is the max. Whatever function value is the smallest is the minimum. It is okay to have the maximum or minimum occur at 2 different values. Because remember, the maximum is actually a y value. So that height could be met at several places. So the maximum could occur at different x values, but there's only one maximum, right? Because the maximum is the y value. I can't do this one because I don't know how to do natural logs. In my head, I can guesstimate, but I don't know for sure. But you just plug these in, and the biggest is the max and the smallest is the min. I know the max and min are out there. They have to be either at the endpoints or a critical point. This is the only critical point in the interval, so it's got to be at one of those 3 spots. Questions? Any questions on that?
It is good. It's clear.
Okay, good.
Thank you.
I mean, I would say there's, when I think of these questions, there's always, to me, there's 2 parts. There's the calculus part, the like idea, conceptual part, and then there's like the algebra part, which is like actually doing it and getting the values. The calculus part is understanding this sort of why this works and what we're doing here with these pieces. And then the algebra part is, I guess the calculus part's also taking the derivative, but most of these derivatives are hopefully pretty easy for us. The algebra part sometimes is hard to solve some of those equations. So that can often be the hardest part of this problem in terms of an individual step. But really the challenge for most students is just linking all of these ideas together into, that's how we attack those problems. Okay? Each of the steps are pretty straightforward, but putting them all together is not, especially in the beginning. Any other questions? Okay. I think those 2 questions, did cover, like if you look through it, a lot of them are these closed interval method problems, like about half of them are kind of these closed interval problems. And are all the rest of them? Well, almost all the rest of them are critical number problems, right? So it's that very similar process throughout really all the problems, but you will see some different types of equations to solve. So that's something to be aware of and pay attention to. Okay. Okay, any other kind of conceptual or specific questions from 4.1? If that's a good thing or not, but It's really, I mean, again, once you get the idea of it, it really comes down mostly to just solving the equations that you get and a little bit of taking derivatives. Like I said on Tuesday, you got to make sure you get the derivatives right, because if you mess up the derivative, then you're going to spend all this time trying to solve it. You may not get something you can solve. Your answers won't be right. And it'll all come back to just the little error made on the derivative. So really make sure you, even if it's fairly easy or it looks easy, just take your time with the derivatives and get those correct. I see that on homework assignments and exams, and oftentimes there are ones that you really know you just made a little error or rushed through them or something. So, okay. Well, I think that's everything. Well, let me just do one little example of why this condition that the function is continuous is so important. Imagine we had a function that looked like this. Yeah, that'll work. And let's say we were trying to find the max and min of this function on the interval 1 to 4. If we didn't know what the function looked like, and we just tried to use the closed interval method here, we would take the derivative of the function. This isn't lined up very well, which is kind of my issue, right? My beef. Let's just say that's a 2. Even though it's not, right? What we would find is when we take the derivative that f prime of 2 would be, since there's a discontinuity there, it can't be differentiable. The derivative doesn't exist, so f prime of 2 does not exist, which would imply that it's a critical point. Right? It is a critical point. The function exists there, but the derivative does not. So we have a critical point. And so what we would do then is we would say, remember, we're just going through our closed interval method like we did in the last problem. We'd say, okay, I've got one critical point. I've got these two endpoints. I'd check f of 1, I would check f of 2, and I would check f of 4. Right? They're only integer values just because I'm trying to make our life easier, right? I mean, there's infinite values in there. Sometimes will be all kinds of different things, right? But in this case, it ends up 1, 2, and 4 are only possibilities based on the theory. And what I would find is that, and again, it's a little tight here, but f of 2 certainly looks like it's a little bit bigger than f of 1. So let's say, you know, f of 4 is 1, f of 1 is 3, and f of 2 would be 4. So what we would say then is we would say, okay, this is the max, and this is the min, and we're done. Right? Now clearly from the graph, that is the wrong conclusion. Right? That is the wrong conclusion because all of these values are certainly bigger than 4, right? And so this is not actually the max. The information that we would get is incomplete and incorrect because we started off with a false assumption. And the false assumption here was that we assumed that there is an absolute maximum and a minimum. In this case, there actually isn't an absolute maximum or minimum. And so it certainly, you know, we found something that didn't exist because we assumed it was out there. Because there's an open circle here at the top, this function actually never gets to that open circle, so there is no largest value of the function. This has no absolute max. We saw one on Tuesday, I think that was like an asymptote. That one pretty clearly doesn't have a max or min, but it turns out that an open circle like that at the top is also not a max. the function values get closer and closer and closer to this open circle, but they never actually get there. So I can't like pick a number that the function is always less than or equal to. I mean, I can find a number, but I can't find a function value because the function doesn't get there. Does that make sense? It's a weird thing about numbers, right? There's no like number that's just below what this open circle is. There's always like a little space in there, so you can get smaller and smaller and smaller. So that might, if you think about that carefully, maybe that will keep you up tonight when you try to go to sleep, I think, right? It's kind of a strange thing, but the result of that is that there's no absolute maximum. So this goes back to that idea that you have to be working with a continuous function on a closed interval in order for this technique to work. It doesn't work if you run into some other situations. And again, that's not going to come up and trip you up just because we're trying to be friendly to you, I think, in the beginning, and you're focused on learning the process. But I want you to make sure that you understand that the process only works for these certain situations. And yes, when we deal with infinite things, it is often a little confusing and maybe counterintuitive. So if they feel, I don't know, I think in the beginning, it feels like a foreign object, like not a natural idea, some sort of foreign idea. It takes a while for that idea to sort of make peace with that idea sometimes. So that's okay, that's part of the process. All right, any questions on this kind of counter example? And I'll also just say that, you know, this is an example where you're potentially going to get yourself in trouble if you focus on just following like the steps without understanding why those steps work. And that, I think for some of you, usually that's a change that can be hard. You may have been very successful in previous classes by just kind of following the steps really well. Like you have a good memory and you pay attention and you practice a lot and you just can kind of follow the steps and you end up with the right answer. But in calculus, that tends to fail because there's so many different routes to get to an answer that you can't be content with just following steps. That's a good start if you're stuck or confused. Definitely kind of try and follow a model and kind of copy, right, the steps, but you've got to work past that so that you understand why those steps are happening. And that's important here and anything moving forward, that we have a better understanding of why we're doing these steps. And 4.2 is definitely more theory. You can see it already than chapter 3. Chapter 3 was very much kind of like what you're used to. Do this thing, right? Find this derivative, and it is kind of a follow the steps process. And for some of us, that's probably was kind of comforting. But chapter 4, we're getting more into this concept and idea part. So, all right, enough chit chat here. 4.2 is introducing two theorems. It's the mean value theorem and Rolle's theorem. What these provide some of the foundations for what we will do later on in chapter 5. We don't use these theorems sort of directly to help us with things that we're doing, but they are, again, kind of useful down the road. So I do prove both of these, or, well, I think I proved Rolle's theorem in the lecture videos. So I would encourage you to watch that, as I always do. If you know Rolle's theorem, then you can kind of get the mean value theorem for like half off. It's like you've done most of the work with Rolle's theorem. So in some ways, it's well, it's easier to prove, but the mean value theorem is a more useful statement. So I'm just going to state both of them here and talk through their implications, but you should look at the proof to help you understand where they come from as well. We'll start with Rolle's theorem, and it says it has some conditions. So like any theorem, you got to meet the conditions if you want to get the conclusion. Rolle's theorem says if f of x is continuous on the interval a to b. So that's number one. You got to meet these couple conditions. So it's got to be continuous. We know what that means, right? Solid endpoints, no jumps or hops in between. That's the way we think about it, even though we know continuity is a little more subtle than that. It also has to be differentiable. So differentiable just means that the derivative exists, the value of the derivative exists. Not like I can write down the derivative. I mean, I guess that's important too. I have to be able to write it down. But really what we're talking about there is that I can plug in a value and the derivative exists. So it's not undefined. The derivative is not undefined. We can't be differentiable at a solid endpoint like this, right? Because the derivative, remember, needs to look at both sides of the function. So I can't say it's differentiable on the closed interval. The best I can guarantee is that it's differentiable on the open interval. So the open interval would look like this. And it turns out if you have an open interval, then you can always look on both sides. There's like a little space no matter what number you pick. Kind of back to our previous discussion of infinity earlier, right? So I don't know that this distinction is going to come up for you in some fundamental way, but the conditions are slightly different. So continuous on a closed interval, differentiable on the open interval, and f of a needs to equal f of b. So if you can meet those three things, then there exists a C value in the interval A to B such that f prime of C equals 0. So, well, I don't know. I don't know what impact this has on you. I couldn't hear audible gasps of surprise. It's not perhaps that surprising, but and we'll talk about it, because I think when you read a theorem like this, it's like, well, okay, I can read the words you wrote down, but there is no meaning there, right, till we add something to this. But I think that the result here is kind of impressive in that the derivative equals 0. Those are important points. That's where the slope is 0. Those are possible relative maximums or minimums. Those are sort of like very desirable sorts of things to find. And this doesn't tell me actually how to find it. It just says it exists. It's out there. Somewhere there's a spot where the derivative is 0 if you meet all these conditions. So that's useful, right? Just like before, it was really important to us to know that there was a min and max so that then we could go out looking for them, right? And find them. And that was actually pretty important. it's a similar idea here in that knowing the derivative equals 0 somewhere tells us some kind of important stuff. So let's just visually get a sense of why this theorem is working. And like I said, I don't want to go through the whole proof here because I redo it and the lecture videos. But, you know, I'm looking on a closed interval a to b. My function has to be equal on the endpoints. And then from there, my only restriction is that it's continuous and it's differentiable. So differentiable means there can't be any like sharp corners or things like that. And continuous means there's no hops or jumps. And the idea is it's a little bit like an art project. Like if I go up at all, ever, if I go up, then all of a sudden these endpoints aren't a maximum anymore. So I must have a maximum because it's continuous on a closed interval. That maximum has to occur at a local maximum, but since it's differentiable, the derivative actually has to be 0 because that's our rule. If I have a local max, the derivative is 0 or undefined, but it's differentiable means it's never undefined. So these rules here, conditions kind of trap us into the situation where, you know, if I go up, I got to come back down at some point. And as soon as I come back down, it turns out that derivative there has to be 0. So that would be the value of C that was guaranteed by this theorem. You can have multiple C values where the derivative is 0, that's fine. But you have to have at least one. That's what this theorem is saying. Yeah, I mean, there is a relationship there to the squeeze theorem. You know, there's these, you know, it's maybe bigger picture in terms of like there's these conditions and then you get this result, and the result is sort of telling us, in the squeeze theorem, it's sort of telling us about the limit. Here the result is telling us about the derivative. But yes, it's sort of like meeting these conditions sort of locks us in the same way the squeeze theorem does to this result. The derivative has to be 0 somewhere. And it's called an existence theorem because it doesn't actually like help me tell me where it is. I still don't actually know where it is. I just know it's somewhere in that interval. And turns out somewhere is a lot better than knowing it exists somewhere is a lot better than not knowing it exists. It's a big improvement. So if you want to use Rolle's theorem, you got to meet these 3 things. You got to check them. And I will tell you that the one everybody messes up is differentiable. People will take the derivative, like if my function is, a classic example is x to the 2/3 on the interval like -8 to 1. So a question might be, can you use Rolle's theorem? And a lot of people will say, oh, okay, well, is the function continuous? Sure, the function's defined. You can take the cube root and square it of any number. So the function's defined everywhere. Is it differentiable? Well, I'm going to take the derivative here. Oh, the derivative exists, right? I can take the derivative, so it's differentiable. Wrong, right? That's just what we said was the problem, right? It's not that you can take the derivative, it's that this function exists on this interval. And if you rewrite this function without negative exponents, like you should, then you'll see pretty quickly that x equals 0 is a problem. It does not exist at x equals 0. So this implies no Rolle's theorem. It's not differentiable. There's a value where the derivative doesn't exist. It might just be a sharp corner. In this case, it's a sharp corner. But it could be, who knows? If the derivative doesn't exist, though, all of a sudden Rolle's conclusion is not guaranteed. You could have a spot where the derivative is 0 too, but maybe not. And the sort of visual example of that is like if your function from A to B, if your function does this, well, see now that's a continuous function. It's not differentiable right here. And the derivative, it turns out, doesn't equal 0 anywhere because it goes up, 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 and then it just has the sharp, the derivative undefined and goes down, down, down. So, right, that's why this differentiability clause is important. Without that, we wouldn't know that the derivative is 0. Okay, so maybe even a little more than I was planning on Rolle's theorem, because the mean value theorem is actually the more important of the two. They're very similar to one another. MVT, mean value theorem. It says if f of x is a continuous on the closed interval a to b, and b differentiable on the open interval a to b, and you should be thinking, you get stuck in a little glitch because this is exactly the same as Rolle's theorem, and this part is, but I don't need the endpoints to be equal. All I need are these two conditions. Then there exists a c in the interval a to b. So same idea here as Rolle's theorem, but if I don't know the endpoints are equal, then my guarantee is a little different. There exists a c such that f prime of c, it may not equal 0 here, but I can guarantee that it equals f of b minus f of a over b minus a. And don't get thrown off because it looks like a lot of symbols and letters. You know what that is. That's just the slope between those 2 points. So what this says is that the derivative is equal to the slope between the 2 endpoints. And the visual idea for that one is that if this is my a and b, my function might do something like that. And so somewhere in here, right, that slope equals that slope. So this value of c, right, would be the guaranteed value from the mean value theorem. And certainly, notice if f of a and f of b are actually equal to each other, like in Rolle's theorem, if that happened to be the case, then f of b minus f of a would be 0, and we get that we guarantee the derivative is 0, which is exactly Rolle's theorem. So the mean value theorem takes care of the Rolle's theorem case as well as all the other cases where the endpoints aren't equal. So you don't need to know Rolle's theorem. You can really answer everything using the mean value theorem. I guess you need to know it if it asks you what are the conditions of Rolle's theorem. But if you're actually using it, mean value theorem will give you the same thing that Rolle's theorem would. And I think this sounds very abstract. I'm sure I did the same example in the lecture, so I apologize. I don't always have new material, but it's a good example. It's worth repeating. If you drive, I think it's from like Northfield to Duluth, it's approximately 300 miles. It's not quite, but it's close enough. Oh no, that's not right. It's nowhere near 300 miles. What am I thinking? Sorry, I have my numbers all wrong. It's not even approximately 300 miles. Let's say it's approximately 180 miles. That I think is relatively close. If it takes 3 hours, did you ever go exactly 60 miles per hour. Now, a lot of people will say, well, probably. That's not the question. I'm not interested in probably. That's something for a statistics class or something else. But this is calculus, right? Did you ever go 60 miles an hour? Can you guarantee that you went 60 miles an hour? Well, what this really is a mean value theorem question. If we think about what's happening here as a graph, where this is my position function as a function of time, I started out at 0 in Northfield, and I ended up at 180 miles in Duluth. Now, how I drove is unclear, right? It's quite possible that I started off and I was just going kind of slow through Northfield, and it took me a while. It was traffic in the cities, and then as soon as I got out of the cities, all of a sudden I decided, okay, now I've got to speed up a little bit, right, to get myself to Duluth. So what happens here is that in the beginning, my rate of change, or my slope of this position function, is certainly less than this slope, right? And notice this slope is going to be total distance over total time, which is 60 miles per hour. So my average speed was 60 miles an hour. I started off slower than average, but at some point here, my speed was 60, right? At some point I went over 60 and was possibly speeding, right? But at some point in there, I was going exactly 60. It would also, of course, be possible that maybe I was, there was no traffic on the road and I set my cruise control at 60 miles an hour as soon as I started, and I just stayed at 60 miles an hour the whole way, right? That's certainly possible too. In this case, right, lots of times I was going 60 miles an hour. I might have started off going really fast and then gone much slower and gone really fast, and, you know, I guess I wouldn't go back down, right? I probably didn't go in reverse. I just went slower. Maybe I took a long extended lunch break, right? And then went really fast and slow into town, right? I could go lots of different ways, but since my driving here is a both continuous and differentiable function, that means that there is at least one spot where my average rate of change is equal to my instantaneous rate of change. That's what the mean value theorem says in an applied sense. Your average speed is equal to your instantaneous speed somewhere, maybe many places, but at least somewhere. And that's why it's called the mean value theorem, right? Because it's mean as in average, not mean as in unfriendly, right? Mean value theorem, meaning it's an average value, right? But it's the rate of change that we're talking about, not just the value of the function, okay? So I do think that this image is useful. You do need to know these conditions and the conclusion. The conclusion maybe seems like a lot, but if you think of the picture, you know, the slope of this line, you can just figure that out. You don't need to memorize that, right? You just need to know that that's the slope of the line, and then that's just the derivative. So the instantaneous rate of change equals the average rate of change. It's not just for position, right? It's for any function if you're looking at its rate of change. Questions about that? See, now you have something to think about at night when you're trying to go to sleep, and also something to think about when you're on a long road trip, right? How position and velocity are connected, and what you can say about those given some assumptions. Okay. Any questions, comments, concerns? Okay.